All right, this is section 4.2, slope of a line. And so slope is the rate of change between any 2 points on a line. It's the measure of the line's steepness. So I'm sure that you guys used a little bit of slope last year. You may not remember everything about slope, but you probably remember the phrase rise over run. And that's what slope is. It's a ratio or a special kind of fraction that relates two different things. And what we're relating is the change in the y, which we call the vertical change, to the change in the x, which we call the horizontal change. And that's why we call it rise, because you're rising vertically over run. And we'll talk about that more as we continue on. What I wanted to show you, though, is that it's any 2 points. It says any 2 points up here, right? So it's not just the 2 points that they highlight for you, but there's any 2 points on a line. So if we look at this next problem, it says find the slope of a line using the 2 black points and then find the slope using the 2 pink points. What do you notice? Well, if I look at the 2 black points first, if I count my rise, and it doesn't matter which point I start at, I'm just going to happen to start at the one on the left here. If I count my rise is 1, 2. And since I'm going up, that's a positive direction, so positive 2. And then my run is 1, 2, 3, which going to the right is also a positive direction. I say that because going to the right is the positive side of the number line, whereas going to the left would be the negative side. So if I put my rise over my run, I get the fraction 2/3. All right, so let's do the 2 pink points and see if we notice anything. If I do the 2 pink points, my rise is 1, 2, 3, 4, 5, 6. And then my run is 1, 2, 3, 4, 5, 6, 7, 8, 9. So my rise is 6 and my run is 9. But just like all of the fractions, which slope is a ratio, that makes it a fraction, slope must be reduced if it can. And so 6/9 actually reduces to 2/3. So what we're seeing here is that regardless of which 2 points you use on your line, you're going to get the same ratio for your slope. It's always rise 2, run 6. And you actually can see that right here. Rise 2, run 3, puts you right there. Rise 2, run 3, rise 2, run 3. That's what you're doing all the way across this line. Whether you're rising 6 and running 9, doesn't matter. You're rising 2 and you're running 3, just doing it multiple times. So as we just said, the slope of a line is the same between any 2 points on the line because lines have a constant rate of change. That's what lines are. They're constant. If it was a curve, some sort of curve like this or like that, it'd have what we call a variable rate of change, meaning it changes at different rates in different spots. You can see on this curve it barely changes, then it starts to change, and then it changes really fast. So that would be a variable rate of change, but lines are just constant. It's always the same. And the slope, m, of a line is the rate of change, as we mentioned, the change in y, the rise, to the change in x, the run, between any 2 points on the line. And those points would be x1, y1 would be the first point, and then x2, y2 would be the second point. And we actually call the slope m. This will come into play later on in this chapter, especially. Just for right now, know that the slope, the variable that we use for slope, the variable we use is m. Okay, and so m is going to stand for rise over run, the change in y to the change in x. In this model, you can see just how that's done. You can see there's a green line up here with 2 points on it. And to calculate the rise, they've done the rise in red. You find what the vertical change is. And you can actually do that, and we're going to do this later, by subtracting the 2 y coordinates. You can see they chose y2 because y2 typically is the second point, and the y coordinate would be greater than the first point because it's higher up. And then to find the run, you could also subtract the 2 x points, and you have to do it in the same order. So if you're doing y2 minus y1, you would then have to do x2 minus x1. And we'll talk about that later because we're going to use that when they give us 2 points that haven't been graphed. We can still find the slope from those 2 points without having to graph them. But if we do have a graph like this one, it's really easy just to calculate what the rise is, what you're counting by, and then what the run is. And you just make that a fraction. Okay, so m equals rise over run, which is the change in y over the change in x. And let's see, they've got a couple examples we can look at here before we start our own. You can see in this example, they calculated the rise in red to be 5, and they calculated the run in blue to be 6. So my slope is 5, 6. In this example, they calculated the rise to be -3. Now, the reason that's -3 is because when they started at this point here, they counted down, and going down is a negative direction. So you have to put that. Now, over here, when they calculated the rise, they went up, which is a positive direction, and they went to the right, which is also positive. So you can see how they got +5 over +6. Over here, we're going to get -3 over -2. I'm sorry, +2. Shouldn't have said -2. +2 because we're moving to the right, and that's going to give us the fraction -3 halves, -3 over 2. If I would have started from the other point, just to make this clear, if I started from this point, my rise would now be +3, but my run, because I'm going to the left now, would be -2, and my fraction would look like this. And it doesn't matter, because as long as one of the numbers is negative, my answer is negative. Think about if this was a division problem. If I asked you to divide, it wouldn't matter which number is negative. Your answer is negative. In fact, you could just put you could just say it's -3 halves. You could put the negative in the middle. If I look at the other example over here, you can see if I start at the top right point, if I calculate my rise, I'm actually going down 5 this time. And if I start from that point and then go this way, I'm actually going left 6. So my slope would be -5 over -6, but two positives or two negatives make a positive, and you still end up with that same answer of 5, 6. So what I'm trying to prove is that you could start at any point and not only get the same slope, but even if you go a different direction, you're still going to get the same answer everybody else does. Let's do a few examples on our own here. We can see, I'm going to start at this left point. You can start at the right point if you want to. My rise, I'm actually going down 1. So -1 would be my rise over. And then I'm going to calculate my run. 1, 2, 3, 4, 5. So my run is 5. So my slope is -1/5. For the next example, if I start at the left point, my rise is 1, 2. And then my run is 1, 2, 3, 4, 5, 6. So rising 2, running 6. But I don't want to leave that as 2, 6. I want to change that to 1/3 because I'm going to reduce that, and I want all my ratios to be reduced. Example C, I'm going to start here at the left point. I just like to start at the left point, wherever that's top or bottom, doesn't really matter. I just like to start at the left. I'm going to rise 1, 2, 3, 4, 5. It's a +5. I'm going to run to the right, making this a +2. So my ratio is 5 over 2. Now, we're going to leave that as 5 over 2. We are not going to write that as a mixed number. I see that as a common mistake. And the reason we don't want to write this as a mixed number is because slope is a ratio. So it's like a fraction, but it also doesn't have all the same properties. We don't want to write it as a mixed number because then you have 3 numbers that you're relating, and a ratio just relates 2, a rise 5 and a run 2. So we don't want to change it to a mixed number. Also, another common mistake that I see is writing it as a coordinate point. Slope is not a location. Slope is actually the directions to the next point. It's not your location. In fact, the 0.52 would be somewhere off up here, right? And that's not even close to our line. So it's not a point, it's a fraction, it's a ratio that tells us where the other points on our line are going to be. Okay, here's an interesting example here in example D, because they give us a point 1.5 up here. I'm still going to start at the point on the left. I'm going to calculate my rise. 1, 2, 3, 4.5. So 4.5 is going to be my rise. And then I'm going to calculate my run. 1, 2, 3, 4, 5, 6. And that's a +6. So I've got 4.5 over 6. Now, that's not going to be an acceptable slope because it's got a decimal. We don't like fractions that have decimals in them. So here's a really easy way I could get rid of this decimal. You'll notice that it's 4.5. And so I could just multiply the top and bottom by 2. It'd be really easy to do. And 4.5 times 2 is 9. And 6 times 2 is 12. And what I've done is I've kind of unreduced it, if you will, expanded it. I don't know what the opposite of that would be. I've reversed, I've made it bigger so that the decimal's gone. And then now I have this fraction 9/12 that I can easily reduce the correct way by dividing by 3 and make it 3/4. So the slope that I want to use for this line is 3/4. And watch what happens if I start again at this red point and calculate my rise of 3, 1, 2, 3, and my run of 4, 1, 2, 3, 4. I'm right there on the line. You'd think, why didn't they just use that point? Well, I think they're trying to prove the point you could use any point on the line, even if it's a half a point right there. Not very friendly point to choose for us, but it is a point on the line, and we can still calculate the slope from it. On example E, it looks like they've done the same thing, but they're actually counting by 2's on the y-axis. So just keep that in mind. They're not counting by 1's like they have been. So when I rise up here, that's going to be 1, 2, 3. So my rise is 3, and my run is still going to be 1 because they're counting by 1's on the x-axis. So they've only scaled the y-axis differently. So my rise is 3, my run is 1. That actually can reduce to just 3. It's okay to reduce your slope to an integer, like 3. We just don't want to write our improper fractions, like 5/2, as mixed numbers. Don't write it as a mixed number, but you can reduce it to an integer. And then we get to two interesting examples here in F and G. In example F, there actually is no rise. The points are directly across from each other, so the rise would be 0, and the run would be 1, 2, 3, 4, 5, 6, 7. So then I would have the fraction 0 over 7, and then 0 over 7 would actually reduce to 0. So what I guess what I'm trying to say is anytime, it doesn't matter what your run is, they could have chosen this point right here. It would have been 0 over 2 now. It doesn't really matter. Anytime we have a horizontal line, our slope, our m, is always going to be 0. Anytime we have a horizontal line, any horizontal line, the slope is 0. It's flat. You may remember that from last year. I think you guys might have talked about that last year. Also, you might have talked about this line here in example G. If I calculate my rise, 1, 2, 3, 4, positive 4. If I calculate my run, there isn't a run, so it's over 0, but there's a problem with that. I can never have 0 in the denominator of my fraction. That means I would be dividing by 0, which we also know is incorrect. So anytime we've ever been told to divide by 0, we've always written undefined, which we can abbreviate. I'm okay if you abbreviate UNDF, undefined. So anytime we have a vertical line, it's going to have an undefined slope, whereas a horizontal line is going to have a 0 slope. Now, don't say that example G has no slope. That's not true, okay? Because no slope would mean 0 slope. That's what the word no would mean. If there's no slope, you'd say it's 0. It has to be undefined. You have to call it an undefined slope so we know the difference. And I threw this last question in here because I wanted to give you guys some extra, kind of relate this to the 4.1 lesson that we did. It says, what are the equations for the lines in example G and H? Well, if you look in your notes for 4.1, we know that any horizontal line is going to start y equals, and then whatever the spot it crosses the y-axis. So since this line crosses the y-axis at 5, right up there, the equation for this horizontal line is just y equals 5. All horizontal lines will start y equals and then a number. And then for example G, all vertical lines will start with x equals. And then wherever it crosses the x-axis, which right here crosses at 4, positive 4. So the equation for this line in G is x equals 4. And I know you guys had homework problems like this in your section 4.1 homework. Okay, so just to summarize, the slope of every horizontal line is 0, and the slope of every vertical line is undefined. And here's a nice little chart that shows all that. So lines that go from uphill from left to right, this would be going uphill from left to right, are always positive slopes. My rise is going to be positive, my run is going to be positive, or my rise is going to be negative, and my run is going to be negative, which still makes a positive. Double negative makes a positive. So if it goes uphill from left to right, it's always going to be positive. And if it goes downhill from left to right, it's always going to be negative. So my rise is negative, my run is positive. Make these a little bit nicer. There we go. Or if I start down here, my rise is positive, but my run is negative. So there's always one negative regardless of which way I go. So positive slope versus negative slope. And if it's flat or horizontal, it's a zero slope. And like we just said, and if it's vertical, it's undefined. So those are the 4 types of slopes you'll see: positive slopes, negative slopes, zero slopes, and undefined slopes. Okay, so now we're to the point where we're going to figure out how do we find the slope from 2 points that aren't graphed. So slope we know is the ratio rise over run, which makes it really easy to calculate when the line is graphed. But slope is still the change in y over the change in x. So as I mentioned earlier, if the points aren't graphed, all you have to do is subtract the y coordinates and subtract the x coordinates to figure out what your rise is for the y's and what your run is for the x's. So that's what we're going to do. Slope is y2 minus y1 over x2 minus x1, and that's kind of our slope formula. So if you hear me refer to the slope formula, that's what we're going to be talking about. Okay, so let's practice finding the slope if we just have 2 points. This might be new for you guys this year. I don't think you guys did this last year. So again, we're going to use the slope formula, which is y2 minus y1 over x2 minus x1. And then we're just going to go up here. I'm going to label. I don't need to do this every time, but just to give you an idea, this would be x1. This would be y1 for my first point. This would be x2 and y2 for my second point. So when I say y2 minus y1, I'm going to do negative 1 minus 5. So right, negative 1 minus 5 all over. And then when I say x2 minus x1, I'm going to do 6 minus negative 3. 6 minus negative 3. And now let's simplify this. 1 minus 5, negative 1 minus 5 is negative 6. And 6 minus negative 3 is the same as 6 plus positive 3, which is 9. And then that's going to reduce down for us nicely to negative 2/3. So I don't need a graph to actually find the slope. I can just use my slope formula. So in this one, I've got x1 and y1, and I've got x2 and y2. Let's do y2 minus y1, negative 2 minus negative 2 over. And then I've got x2 minus x1, 7 minus 1. Negative 2 minus negative 2 is the same as negative 2 plus a positive 2, which is 0. And then 7 minus 1 is 6. But you know what? 0 over 6 is just going to reduce to 0. And that means this is going to be what type of line? It's going to be horizontal, which you can double check that because I've got the same y coordinate for both of them. So here's 1, negative 2, and then here would be 7, negative 2. They'd just be right across from each other. So a zero slope. If you feel like you can try example C and D on your own, pause the video and see if you can get them in your notes by yourself. Okay, if you've given them a shot, let's see how you did. So y2 minus y1 would be 0 minus negative 3, which, you know what, from now on, every time that happens, I'm just going to write 0 plus 3, right? 0 minus the negative 3 would just be 0 plus 3, over, and then x2 minus x1, negative 3, minus negative 3 would just be negative 3 plus positive 3. And so 0 plus 3 is 3. And negative 3 plus 3 is 0. And this would be an undefined slope, right? So these points are right above each other to make a vertical line. So it would look something like this, right? You've got negative 3, which would be right about here. And then you've got negative 3, 0, which would be right about there. And these points are right above each other because they have the same x coordinate but different y coordinates. So very opposite of what we were just talking about with example B. And then in example D, y2, negative 2, minus y1 plus 1 because I know negative 2 minus negative 1 is just negative 2 plus 1, over x2 minus x1. Negative 2 plus 1 is negative 1. 6 minus 8 is negative 2. Two negatives make a positive 1/2. So I do need to reduce this to a positive 1/2 for my slope for D. So the next thing would be how to find the slope from a table. So since the points points on the line lie on the same line, you can plug in any 2 points into the slope formula, which we know is y2 minus y1 over x2 minus x1. So when we look at this example, it says the points in the table lie on a line. With this information, the fact that they do lie on the same line, remember we can use any 2 points. So I could choose the first 2 points. I could choose the last 2 points. I could choose the middle 2 points. I could choose any of those. So why don't we just, for I guess right now, choose the first 2 points. Y2 minus y1 would be, let's see, y2 would be 6 minus y1 would be 8 over x2 minus x1 would give us 6 minus 8 is negative 2, and 4 minus 1 is 3. So we get negative 2/3. And we're going to get negative 2/3 whether we do that or even if we did the first and the last one. All right, so if I did 10, oops, not 10, sorry. If I did 2 minus 8 for my y2 and my y1, and then I did 10 minus 1 for my x2 and x1, that's going to give me negative 6 over 9, and that's still going to reduce to negative 2/3. Here's an easier way. I like to do charts, by the way. Charts make it really simple for you. So I like to see, okay, what's happening to my rise? My rise, it's going down 2, right? Every time it seems to be going down 2. What's happening to my run? Well, it's going up 3. So I put plus 3, and then my rise and my run, just do that. You actually don't have to write it off to the side like this if you have a chart. So for example, B, if I do that, my rise is going up or down? Well, it's going down. So it's going down 2. And then my run is going up or down. Now be careful, this is actually going up because it's getting less negative, and it's going up 1. So my rise is negative 2, my run is 1, and that's just going to reduce to negative 2. The next example says, is it more difficult to walk up the ramp or walk up the hill? So the steepness of both of these, remember, can be measured by the slope. So if I do the slope of the ramp, the rise is 6 and the run is 8, and that's going to reduce to 3/4. If I do the steepness of the hill, the rise is 8, the run is 12, and that's going to reduce to 2/3. So then I have to think, okay, which is bigger, 3/4 or 2/3? You might already know this one. If you don't, the easiest way might be to think what these are as decimals. 3/4 would be 0.75, but if you do 2 divided by 3, you'll get 0.6 repeating. And so 0.75, having a 7, beats having a 6. So 0.75 is bigger. So the ramp is actually steeper. Oops, back that up. Is steeper because the slope is higher than what the hill is. You could also make them have a common denominator, but making fractions have common denominators is nobody's favorite thing to do. If you did, this would be 9/12 for the ramp, and it would be, if I times by 4, 8/12 for the hill, and you can see the ramp is still steeper. So the ramp has a slope of 3/4, which makes it steeper than the slope of 2/3. All right, and then our last example says the graph shows the amounts you and your friend earn babysitting. Compare the steepness of the lines. What does it mean in the context of this problem? Well, it's obvious that the blue line is steeper than the green line, but the blue line represents my friend, and the green line represents us. So what do you think that means? Well, if we're comparing dollars per hour, that means my friend is making more money per hour, right? Makes more money per hour than I do. Now, I could be babysitting for longer and eventually make more money, but my friend has a higher rate of earning, right? They have a higher rate of earning, which is why their line is steeper. So it wants us to interpret what that slope actually is. Well, if we start with our line, the green one, we can use any of these 2 points. We could use this one, or you could even use this one, That one's just kind of hiding there. It's 0, 0. That would be really easy to use. So if I do y2 minus y1, I'm going to go ahead and use 0 as my y1. And if I do x2 minus x1, I'm going to use that 0.00, becomes my x2, I guess, or x1. Then I get 20 over 4, and so 20 over 4 reduces to $5 per hour. Now, how did I know to label it like that? Well, since I know that the y value is on top and the x values are on bottom, the y is dollars and the x is hours. So I knew exactly that it had to be 5, not hours per dollar, but because it's y over x, dollars per hour. And that just makes sense. So if I calculate my friends doing the same way, 28 minus 0 is 28 over 4 minus 0 is 4. So in the same amount of time, 4 hours, I make $20, but my friend makes $28 in 4 hours. So their unit rate, there we go, unit rate, something you learned before, is going to be $7 per hour. So now we could tell from the graph that our friend made more money, but then applying the slope formula, we can actually figure out how much more money, right? Our friend makes $2 more per hour than we do.